All right, good afternoon, everybody. My name is Yuanyang. I'm from the University of Tennessee in Knoxville. It is my honor to be here and share with you some of the research projects I've been doing with my colleagues here at the Haslam College of Business, Department of Business Analytics and Statistics. Okay, so I would like to start this talk with the story of your dream life. So what is your dream life, right? For me, my dream life is I would like to travel around the world, visit different places. But I do not have enough money. So to support myself financially to such a lifestyle, my current plan is to make a living by driving Uber. Okay. And then the number one city in my head right now is Barcelona in Spain. This is because I grew up watching Barcelona's soccer team, so they're really my favorite, and it would be great for me to watch them play live every week. That's my dream life, right? But back to make a living by driving part of the story. Do I know the roads in Barcelona? No, I don't. But I would argue I don't need to because I can use Google Maps. Do I speak Spanish? No, I don't. But again, I would argue I do not need to because I can use Google Translate. Actually, what's better, if I join Uber, Uber will tell me exactly where to pick up my customers. So for me, this job of driving is really simple. All I need to do is follow my cell phone and drive from point A to point B, following the specific suggested route. Okay. So this me driving Uber example is really an instance of the so-called Turing transformation process. And there are two key components of this Turing transformation process. Number one, the researchers argue that technology in general and artificial intelligence specifically has this de-skilling effect in the sense that technology may simplify the work that we do as people. And then as a result, technology may lower the barriers to job entry. So again, the whole point of this story, me driving Uber in pretty much anywhere in the world, is as a result of technology makes driving taxi simple for people. Okay, that's the first component. And then the second component, as a result of this AI simplifies work effect, then we should see job opportunities open up for more people. So in other words, again, I would argue anyone who can drive reasonably well should be able to make a living by driving taxi in pretty much anywhere in the world. Okay. So in these research projects, we basically utilize data available nationally in the US and see if these two effects are actually happening. Okay. So that's the goal of this research project. So now to do that, we first need to have some kind of measure that links what people do, for example, driving a taxi versus what AI technologies can do. For example, reading the maps on the picture and translate the language for people. Okay. So we want to utilize data specifically to create an occupational AI exposure index or a number to capture the similarity of what people do, what we do in different kind of work, and what technologies can do. Okay. So to construct such an AI exposure measure index, we first quantify what people do using the standard textual descriptions of the over 900 occupations in the US. So this data set is created and maintained by US Bureau of Labor Statistics. So basically the government classifies all the jobs or occupations in the United States into 965 different occupations. Okay, and then for each occupation, there is a text description of the of the work there. Okay, I'm going to show you example in next slide. Right. So this is what people do: textual description. And then to measure what artificial intelligence technologies can do, we utilize a recent data set of AI patents. So patents basically measure new technologies, okay? And then for each of these over 100,000 AI patents, we also collect their textual descriptions, including the patent title and abstract, okay? So now we have some quantification in text in terms of what people do and what technologies can do. And then we feed this text input into a so-called sentence transformer model. So this model will transform any text data into a set of numbers. And then using two sets of numbers, we can calculate numerically a similarity measure. Right? To give you some idea what our data looks like. So here on top of this table, this is the textual description from the government of the occupation radiologist. So this is, again, a standard representation of what radiologists would do, okay? Radiologists, they examine and diagnose disorders and diseases using X-rays and radioactive materials, may treat patients. And what tasks? Well, radiologist needs to obtain patient's history from electrical records, blah, blah, blah. A paragraph of description of a radiologist, okay? And then down here, this piece of text here represents the most similar AI patents that is most similar to radiologist description here out of the 100,000 AI patents, okay? So the most similar AI patents text to radiologist is a system combining automated searches of radiological images, association number assignment, and so on, okay? Right. And then a little bit detail of why do we want to apply this approach, okay? So what does this model do is this sentence transformer will transform any piece of text into a vector of size 768, okay? So this is actually the key that enables our methodology, because now for any text, we can represent them with a set of numbers, and then we can compare the similarity of two pieces of text with a specific numeric representation, okay? So let's try to see that with a very simple example. So in this example, I have three sentences: sentence one, sentence two, sentence three. Sentence one, the phone's battery life is amazing. It lasts all day long, okay? So this is a sentence, a text, a small piece of text. And then what this model will do is transform this sentence into a set of 768 numbers, okay? Sentence one. Sentence two, I don't have to charge this device frequently. It stays powered for an extended period. It's a textual description of a phone, okay? And then this model will also transform this sentence into a set of 768 numbers, right? And then sentence number three, my life is amazing with a phone, okay? And again, what this model will do is it will transform this sentence into a set of 768 numbers, okay? So now, what's more here, I highlighted some common words, right? So in other words, sentence one and sentence three have common words: phone, life, amazing. But in terms of understanding the meaning of the three sentences, we can all see that sentence one and sentence two are really similar to each other, because they're all actually talking about the substance of the battery, okay? Sentence one, the phone's battery is amazing, okay? Sentence two, even though it is not mentioning the phone battery, but we can understand, right? We as humans, we understand English, we understand sentence two is also talking about the battery is good, okay? And then sentence number 3, although it has common words with sentence 1, but we can, again, very crucially, we can understand sentence number 3 is talking about something slightly different than sentence 1. It's not talking about the battery life, right? So what we want to achieve is we want to utilize a model that can actually capture not only the common words, but really the meaning of the text, okay? And this sentence BERT model can help us achieve that. So now if we calculate the similarities based on the corresponding sentence embedding vectors, okay, we can see that sentence 1 and sentence 2 actually has much higher similarities versus sentence 1 and sentence 3, okay? So again, in this case, this model can really capture, in a sense, the meaning of the sentences. And sentence 2, although they don't have common words with sentence 1, but it can recognize it's talking about the same thing, okay? So we basically utilize this sentence transformer model for each piece of text, generate a vector representation of it, and then for all the occupations and AI patterns, we can quantify their similarity in meaning, okay? So this is basically how we construct our occupational AI exposure measure. So more specifically, there is a total of over 900 standard occupations in the United States. And then we can calculate for each occupation its average similarity to all the AI patents in the specific granted AI patents granted in a specific year from 2010, 2011, 2012, up until 2018. Okay, right? So this figure shows you the time trend of our AI exposure index. So this gray dot shows you the average AI index trend over all the occupations, over all the 900 occupations, okay? And then this blue line shows you the specific occupation related to production and manufacturing workers. And then the production occupations exposure or similarities to AI patents related to hardware. So in this case, we can see compared to the overall average, the similarity or exposure of production occupation to AI hardware is actually having a stronger increasing trend, okay? Similarly, this green line shows you the AI exposure index for transportation-related occupations, so drivers of all kinds, and what they do versus the computer vision AI technology. So again, here we observe a stronger than average increasing trend for transportation occupation in terms of their similarity to computer vision AI technologies over time. Okay, so this is basically a numeric representation of how similar what we do are to the technology's capabilities. Okay, so this will be one key variable in our data analysis. And then the second key variable we want to have is we want to quantify the changes in the nature of work in general and to the national level over time. So for that information, we collect data from census. So all these are publicly available. So we collect data from census who periodically surveys employees in the importance of these 9 task activities, okay? And then for each of these 9 task group, government will ask a sample of employees, say, okay, in performing your job, how important is, for example, performing complex technical activities? Score it 1 to 5. 5 means very important. 1 means not that important. Okay? Okay. And then because governments conduct such surveys over time, so for a particular occupation, in 2 surveys conducted in different time periods, okay, we can actually calculate the importance score changes across the two surveys. Okay, so imagine me driving Uber, by the way, right? Government will come to me, say, Yang, you are a taxi driver. How important is communicating and interacting in your work? Okay, and then a few years later, they come to me again, maybe say, okay, how important is communicating and interacting in your taxi driving job? Okay, and then they do that for all these tasks over time for all the occupations. And then what we can do is we can connect these two quantities together and examine their relationship. So let's focus on this part here. Remember, the two quantities we have is, number one, this occupational AI exposure. Okay, over time, how important is what I do in terms of similarity to the technology's capability. Okay, this AI exposure. And then number two is this task importance measure. Okay, over time, for the job I do, how important is manual work? Okay, is it becoming more or less important over time? Right. So now, if we can set up this regression model, we have AI exposure measure, we quantify task importance change over time, and then we can also quantify the relationship between these two changes using this regression parameter beta 1. So if this regression model says that beta 1 is estimated to be negative, that means we actually observe a AI de-skilling effect, in the sense that for what I do, when it's becoming more and more similar to AI technology's capability, the corresponding task is becoming not important. Okay. On the other hand, if we observe beta 1, this relationship to be positive, that's basically saying the technologies may lead to certain tasks becoming more important for a specific occupation. Okay. So now let's look at some results. So remember, we have 1, 2, 3, 4, 5, 6, 9 broad category of work tasks. Okay. And then across all the occupations, we run this regression and we can estimate the relationship between AI exposure and the task importance change. Okay. And the estimated results are represented here. Right. So now if we only look at the sign of this estimation, positive or negative, we can see when all occupations are considered, almost for all tasks, there is a negative relationship between the occupation AI exposure versus occupation's task importance change. So in other words, here we actually see some evidence that AI is simplify people's work across a comprehensive set of tasks. Okay, represented again by overwhelmingly a negative relationship here. Right. And then if we look closer, okay, there are about a total of over 900 occupations. And then different occupations, they have different level of skill requirements. Okay, so in this case, we can find a subset of low skill occupations. So those are typically require a high school education at most. Okay, typically a high school education is enough. Right? And at the other extreme, we also have a set of high skill occupations, typically requiring a college or even a master's degree. Okay, right. And then what we see is, from last slide, we see overall there is a AI de-skilling effect. AI make the work simpler for people on average for all occupations. Okay. And then if we look at specifically the low skill occupations, we actually again observe, number one, all negative relationships. Okay, okay. And then number two, the negative relationships size are actually much larger than the average size. So this is suggesting that, again, the overall negative relationship is actually mainly driven by low skill occupations. Okay. And then on the other hand, if we look at the other extreme of high skill occupations, okay, such effect is smaller. And more importantly, we actually see some AI upskilling effects, right, highlighted by red color here. So now certain tasks are becoming more important, probably due to AI technology advances, but only in high-skill occupations. For example, administering, so management related, communicating and interacting to people, okay? Reasoning and decision making, okay? So now if we want to tell a story in terms of communicating and interacting, negative 9.1. Imagine me driving Uber in Barcelona, Spain. Driving Uber, do I need to talk to people? No, I don't need to, because I use Google Translate, number one. Number two, me and my customer all look at the route suggested by the app. So there's no need for communicating, okay? But for certain high-skill occupations, the typical example is radiologist, actually, okay? For radiologists, technology may help them analyze the image, okay? But now what's becoming more important is the part of radiologists' work that they need to talk and interacting with other physicians as well as patients, okay? So similar story can be told in terms of reasoning and decision-making. So again, negative relationship, you might imagine me driving Uber. No, I don't need to make any decision. I don't need to decide which route is best to go. I just follow myself. But for certain high-skill occupations, now technology may provide some information, and then people needs to make better decision or judgment based on the information provided by technology. Okay? So now, at this point, I hope I have at least convinced you with some empirical evidence that artificial intelligence has this effect in simplify the job, the work content for people, at least for a subset of them, okay? And then if we're still thinking about this Turing transformation in general, we have evidence for piece number one, and then next, we want to see how job opportunity outcomes across different occupations are changing along with occupational AI exposure, okay? So in this case, what we can do is we can run a similar regression as I showed you before. And again, in this case, we examine when occupations AI exposure increase, how does the job market outcome change correspond? And in particular, here we consider two job market outcomes. Number one, number of job postings. So this represents companies' demand. They want to hire such people, okay? They post jobs online, right? And then number of employment. So this represents the actual people who are employed or working in a specific occupation, okay? So what we observe here is, again, when we look at all occupations, right? When an occupation's AI exposure increase, we observe correspondingly an increase in the demand as well as an increase in the actual employment. So at this point, I think it is good news, I would say, okay? In the sense that we find empirical support for the two pieces of AI's effects on the job market in general. Number one, technology simplifies people's work. As a result, it lowers the barrier for job entry, which may lead to expanded job opportunities, okay? This is what we observe, at least when all occupations are considered, right? However, if we look at occupations of different types specifically in terms of their skill requirements, so again, if we consider only low-skill occupations, we do not see such job opportunity expansion effect, okay? So remember, when all occupations are observed, there is a positive effect in both demand and actual employment. But if we look at the occupations requiring a high skill degree or less, okay, we do not see such job opportunity expansion. Again, at the other extreme, okay, we observe for those high skill occupations requiring a master's degree specifically. For those occupations, when they become more similar to AI technology, correspondingly, employers want to hire more such people, reflected by the number of job postings, okay? And then what's interesting here is we do not observe a corresponding increase in actual employment. So the difference between these two measures is, to us, suggesting a potential skill gap due to the advances of artificial intelligence technology, but not everywhere, specifically in high-skill occupations. Okay, all right. And then again, to me, and this so far, this is all good news because AI is creating job opportunities. Where are they? Well, they're in high-skill occupations, which typically pays higher salary. It is psychologically more rewarding for people, potentially more fun in general to work in those jobs. Okay, this is all good news, but the key question is, how do we move people there, right? Well, the obvious question is, we should give people education in general, right? So my number one takeaway when I was seeing results like this, my first reaction is literally, okay, if I have an 8-year-old daughter, and then if she asks me, should I go to college? And then my answer is yes, absolutely yes. If you read my paper, you should actually probably want to go to graduate school. But then when they tell me, okay, it's $40,000 a year, I don't have a clear answer to that. Okay, so I guess we know what we should do in the sense that the overarching goal is we want to better reskill and upskill people in correspondence to the advances of technology. But the challenge is what is the best way to do it? Okay, and that is the question I think it takes all parties of a society to work together and figure that out. Right. So, in summary, the key ideas I want to convey is that we examine specifically two sets of AI technology's impact. Number one, again, technology should make our life easier. They simplify work, okay? And then number two, again, it is good to see that, okay, as a result, technology may be creating more job opportunities, but only in high-skill occupations, right? So this is all good news. And then in the next few minutes, and the follow-up study, we actually perform a firm-level analysis in terms of seeing what job requirements employers are changing specifically as they're adopting to these AI and machine learning related technologies. So what we observe is that, okay, when companies are adopting more advanced technologies, they actually increase their job requirements in two aspects specifically. Number one, they require more work experience years written in the job posting text. So to me, this is not good news anymore because that means AI technology may have this impact of diminishing entry-level jobs. And then what's more, I, as a teacher, I can teach you how to program, okay, let's say, how to perform statistical analysis, but I cannot teach you work experience, okay, all right. So that's a challenge for us. And then number two, firms also increase their job requirements in terms of the so-called higher order skills, such as decision-making, critical thinking, problem solving, adaptability, okay? So this should be not difficult to understand if you understand AI's simplified work effect. So that means technologies, they can do something. What they can do, well, they make work simple, and specifically, technologies may be able to handle standard, routine, simple cases. And then what are left for us, the people, to do are the difficult ones. And the difficult ones require us to make the hard decision, think creatively, and maybe think about how can we adapt existing solution to novel and new scenarios. Okay, so this is what we find at the granular firm level. And then again, I think the key message I want to convey here is, and this to me at least, it reinforces this general notion of importance of education as a response to the advances of technology. But again, the challenge is how do we provide workers such knowledge and what knowledge we should be providing. And again, that's a task that takes everybody's effort to achieve. Okay. And thank you all very much. I will stop here and I will be very happy to answer any questions you have. Thank you.